for those of you who don't know me, I'm Michelle Shattuck. I'm a research scientist at the University of New Hampshire and also the Associate Director of the New Hampshire Water Resources Research Center. And I have the privilege of introducing the first block, the first set of speakers today, which I'm part of. And our block is about water quality trends. And we're going to approach this block from the perspective of considering water quality from the perspective of three different types of restoration, three different approaches to restoration. In the first talk, we're going to hear about how changes in wastewater management have impacted water quality trends in rivers to the Great Bay and the estuary itself. In the second talk, we're going to get some insight as to how the Clean Air Act amendments have changed inputs to watersheds over time. And then in the last talk, we're going to get to hear about restoration from an ecosystem restoration perspective. So I'm excited to go ahead and get started. All right, so the first talk is going to be by myself and also Chris Whitney. And together we're going to talk about water quality trends in rivers draining to Great Bay. And I'm really going to focus on the freshwater portion only, and then Chris will take us down into the tidal rivers and into the estuary itself. So a lot of this work that will be presenting is supported by PrEP and partners with the New Hampshire Resources Research Center and UNH. All right, so many of you are well aware that Great Bay has been experiencing, or is New Hampshire's most significant estuary, and it's been experiencing a decline in water quality and aquatic life. We have increased suspended sediments, increased nitrogen, we have a loss of oysters and clams, we have a loss of eelgrass, and also low dissolved oxygen levels at times. In 2009, it was first impaired by nitrogen. And then in 2020, the EPA issued the Great Bay Total Nitrogen General Permit, which was established to reduce both point sources of nitrogen and non-point sources. According to some recent estimates, non-point sources make up the majority of the nitrogen loading to the bay. And then point sources, or those inputs from wastewater treatment facilities, account for about 22%. The watershed is home to about 25% of New Hampshire's population, and it also spans 52 towns, 42 in New Hampshire, 10 in Maine. Okay, so the overarching question for our talk is, is water quality changing in the Great Bay tributaries? Again, I'm really focusing on those the freshwater portion. So here we can see that there are 8 major tributaries to the bay. Their watersheds are outlined in black circles over here. The sampling locations are these black circles all around, and those are located just above the head of tide. So the most downstream portion of the freshwater rivers. And in those 8 watersheds, 4 of the tributaries have upstream wastewater treatment facilities. Over here in the Great Works River, the Salmon Falls River, the Cachiko, these red circles. There are other wastewater treatment facilities down here shown by gray circles in the tidal areas. Again, I'm gonna leave that to Chris to talk about. So we have, I'm having trouble with this pointer. There we go. So we have the wastewater treatment facilities that have had management changes are highlighted in red here. The most significant one being Rochester upstream in the Cachiko River. And then we have river chemistry from monthly samples collected March through December from 2008 to 2023 for this analysis. And I'm really going to be focusing on mean annual concentrations. I'll have some text boxes in these slides looking at export or the mass of nitrogen leaving the watershed on an annual basis, but in the interest of time, I'm not going to really talk about that. The land cover for these watersheds, you can see a lot of green. They're mostly forested, but do span ranges of development in agriculture. So first up, we have the changes in total nitrogen concentrations over time. Again, these are mean annual concentrations from 2008 to 2023. Each slide will be set up like this. And at 7 of the sites, we're not seeing any significant trends. Where we do pick up trends are in the Cachiko River, where in 2014, Rochester introduced pickle juice or acetic acid into their wastewater treatment process, and really had a significant decline in their effluent concentrations. And we can see the results after that, the concentrations are significantly lower. Now, in terms of the fractions of nitrogen, the dissolved inorganic nitrogen tends to be the most responsive to human activities, and we see some varying trends. 3 of the sites where there were no significant changes over time, 4 sites are increasing in inorganic nitrogen, and again, we're seeing decreases in the Cachiko River. There were no changes in the dissolved organic nitrogen fraction. So now let's move on to phosphorus. For total phosphorus, we were seeing changes at 2 of the sites, the Lamprey and the Cachiko, but no change at the other 6 sites. But then in terms of phosphate, or the soluble reactive phosphorus, there were 6 sites out of the 8 that were increasing over time. And I don't think that we've, as a community, been paying as much attention to phosphorus in these freshwater rivers lately, but we do find these trends interesting and probably warrant further consideration. Next, the total suspended sediments. There was no change in concentration over time, at least in terms of mean annual concentrations at 7 of the sites. It was increasing in the Exeter, and again, this is in the freshwater portion above where any improvements were made to the Exeter wastewater treatment plant. But I should note that, again, this is monthly sampling, so it was not designed to capture storms where we might be having a lot more sediments move through the system. So, just a quick summary of this portion of the talk. We've seen that changes in wastewater management have reduced nitrogen concentrations and export in the Cachiko River, that temporal trends of inorganic nitrogen are more variable than the organic fraction and the total nitrogen. Temporal trends of increasing phosphorus, and what I didn't show you was that also results in a decreasing nitrogen to phosphorus ratio. Happy to talk to folks more about that later. So those trends probably warrant some further consideration. And then another thing that I didn't actually have time to show you, but these freshwater tributaries are getting saltier. That doesn't mean much for Great Bay itself, which is a very salty system, but it certainly impacts their freshwater ecosystems in these freshwater portions of the river. So be happy to talk to anyone more about that. And we also have Jeanette from our lab group here today, who is focusing her graduate research on ecosystem salinization. So let's chat if you're interested in that. And some potential next steps, we're working with PrEP. We're really hoping to break down the nitrogen loading to the bay to different set portions of the estuary and not just generate one total load, but look at the sub-regions of the bay, like Great Bay, Little Bay, Upper Piscataqua River, Lower Piscataqua River, and Portsmouth Harbor. Some other work that we hope to do is really start digging into some of the older data back to the early 90s. I found some that are available, and really see how trends are changing over the longer record. So with that, I will hand it over to Chris. These are all over.
So thank you. All right. Thank you, Michelle. So now that Michelle's talked a little bit about the freshwaters, I'm going to talk a little bit what's going on in the estuary. So Michelle and I have been lucky enough to be able to give a talk similar to this to several municipalities. And most of the time, I don't really have the bandwidth for statistics when we're putting those talks together. But for today, I want to kind of delve into this a little bit more quantitatively. So I do have some statistics today. So one of the ways that we assess the health of the estuary is through eelgrass coverage. And as we know, eelgrass has been declining both in Great Bay and at the coast. 2 of the water quality parameters that we're particularly interested in relation to this eelgrass decline is total nitrogen and total suspended solids. So today I'll be talking about TN and TSS sort of in the context of these management decisions. Another map. This one is showing the wastewater treatment facilities and those red diamonds, the estuarine, sampling locations and the black dots. And then I have these estuarine sampling locations classified as either riverine, where wastewater treatment facilities are adding effluent directly upstream. And then there are also these integrative sites, like Adams Point, the Great Bay Buoy, and the Coastal Marine Lab, where the effects of several treatment facilities can be, they sort of coalesce. Data came from PREP's database, the PREP Data Explorer. I did my best to find information about the wastewater treatment facilities and any upgrades that might have taken place, but that information is really hard to find. So I use non-parametric statistics. This is because environmental data aren't typically normally distributed. These non-parametric stats are more robust to outliers, and there are no assumptions about the distribution of your data. Since I was not able to find a lot of good information on the upgrades to the treatment facilities, I used Pettit's test to look for change points in the long-term records, and then Mann-Kendall test to look for trends before and after those change points. So I'm going to get into total nitrogen first here. I realize there's a lot going on here, so I'm going to walk through this figure and hopefully nice and slow so it's easy to understand. The box plots are showing the median annual concentration over time at each of the estuarine sampling locations. The blue vertical dashed lines are the statistically significant change points as determined by Pettit's test. And then we have these red and yellowish lines are the statistically significant trends before and after the change point. And then the green lines are, those are really like the best guess that I could come up with for when sort of changes or upgrades were made to the treatment facilities. All right, so a few things to point out. Change points were detected at, that shouldn't be 7 out of 8 sites, but at all sites except for Great Bay and Chapman's Landing, Lamprey River, sorry. But for the other sites where there was a change point detected, the total nitrogen story is generally positive. So at Adams Point and at the coast, sort of 2 of these integrative sites, we see that increasing trends in TN either disappear or stabilize. At the Oyster River site, there was actually a slightly declining trend that also stabilized. And then at the Upper Piscataqua River site, while it's still increasing after the change point, the increase isn't as severe. So this is a much steeper trend here before the change point than there was after. And so I have this summarized in this heat map, and this should clearly show that, you know, these 3 sites here, Coastal Marine Lab, Adams Point, Upper Piscataqua River, these increasing trends disappeared. And at the Oyster River, the declining trend also disappeared. So it's relatively positive. The total nitrogen concentrations are stabilizing. And then, of course, there were no trends detected at the 2 sites that are on the Squamscott River, Chapman's Landing and the Squamscott River site. So this figure is showing the same analysis, but this is for total suspended solids. Here, all sites showed a significant, statistically significant change point. And the story here for TSS is a little bit different. So we can see at Coastal Marine Lab and Oyster River, these are 2 sites that had stable TSS concentrations before the change point, which began increasing afterwards. Adams Point was slightly, I believe it was slightly declining before the change point, and then after the change point, it shifted to an increasing trend. But then we have the 2 sites on the Squamscott River, the Squamscott site and Chapman's Landing. Those were both trends that stabilized. They were actually decreasing trends that stabilized, and then, you know, no trends in TSS at Upper Piscataqua River or Great Bay. And again, this heat map shows that. So where we see improvements or at least stabilization at the Squamscott sites and at the Lamprey River, but we're seeing increases in TSS concentrations at the coast, at Adams Point, and in the Oyster River. So what does this really mean for water quality in the Great Bay? TN, the story is generally positive. We're seeing a lack of stabilization of trends post change point at 3 sites. And then at the Upper Piscataqua River site, we're seeing an increasing trend become less severe. TSS, we see slightly mixed results. So we're seeing increases in concentration after the change point at 3 sites, but at 3 other sites, we're seeing improvement or at least stabilization. So this suggests that these management decisions are having an effect on the total nitrogen concentrations that we're seeing in the estuary, but there can be more done with total suspended solids. And I think I hit my time right on the money. All right, thank you very much.
Thank you, Chris. Next, I'd like to introduce Clarisse Ishimwe, and she's going to be talking to us about nitrogen inputs to watersheds and riverine exports.
You can use that, or you can yeah, good point. Yeah, you can put it here if you want. Use the mouse pad and use you can use the arrows to advance.
Good morning, everyone. I'm Clarisse Ishimwe, a PhD student at UNH. Today, I'm going to talk about nitrogen inputs and riverine export to one of Great Bay tributaries, Grand Prairie watersheds. So thanks for Michelle. He gave some overview on nitrogen issue on Great Bay, so I will not repeat that. I will directly go to the talk about the nitrogen sources in the watershed. So as we can see, nitrogen have various sources in the watershed. Some can be from atmospheric deposition, some fertilizers, manure from livestock, human waste, or nitrogen biological fixation. But these inputs are greatly influenced by the land use condition within the watershed. And when they reach in this watershed, they have different fates. Some can be uptaken by crops, other can be retained or denitrified back to atmosphere as N2 or N2 or nitrous oxide, and the remaining can move through soil and groundwater and exported through riverine exports. So the balance between inputs, what is retained and what is exported is what determines the nitrogen that reaches downstream bodies such as estuaries. So quantifying these inputs is really challenging because most of these inputs are at large scale. So in this work, we are using a rich data set that is available across the US. It's a data set that is developed by Barnes et al. In 2020 that quantified net anthropogenic nitrogen inputs across the whole US at county level. So here I'm just showing 3 examples of counties that cover Great Bay, Rockingham, Stafford, and York, and it shows all these inputs, and we see that within the county we see the similar trend from back in 1930s to 2017, but we see the major input here is atmospheric deposition, which is in line with the regional trend of nitrogen input within the New England region. However, we see some trends or shifts in these inputs where recent years we see the decrease in atmospheric deposition, but we see a slow increase in input from human and fertilizer, which might, due to the land use change. For example, this is the land use change from 1985 to 2017, where we see that the total development area of these 3 counties have increased, while forest and total agriculture is going down. So as I said, I'm working on watershed scale. So to downscale these inputs from county to watershed scale, I'm using annual national land cover change data set, which is from 1985 to 2024, and then allocate those inputs from county scale to watershed scale. So for interest of time, I will not go to details, but if anyone is interested to know how I did that, I'm happy to share that later. So once we scale down those input at watershed scale, then we can compare them with nitrogen export from available data set. And for this talk, I'm giving the result for Rainprey watershed, but we do this for all Great Bay tributaries that Michelle talked about later. So earlier. So once we calculate the river in exports from nitrogen concentration and stream flow, then we can compare the input and export and see how those are changing over time. So looking at Rainprey watershed itself, we see that we see the same trend as what I explained from county level. Atmospheric deposition is declining over time, but still is the major input of nitrogen input overall. But we see a slight increase in human and fertilizer inputs. So this is like a summary of the above graph where atmospheric is going down, but slowly we see an increase of fertilizer and human. Looking at riverine export, we see that we see that there is great variability of nitrogen export overall, but the main takeaway here is that dissolved organic nitrogen is the most dominant form of N export across all years, followed by nitrate and particulate nitrogen and ammonium. So when we put this together, then we can compare the input and output over time. So on this graph, on first y-axis, I have N inputs, and on the second y-axis is nitrogen export over time. So we are just comparing the years where we have both input and output. So inputs are the black line and export are blue line. So here in this graph, we see that around 2000 to 2005, the inputs are not reflecting the exports. So the inputs are very high, but we don't see change in, we see low export. While after 2006 or to 2017, we see that as inputs goes high, also export goes high. So we see some coupling and decoupling between inputs and export. However, when you look at it in overall, we see a very positive relationship between nitrogen input and riverine exports overall. So this means that as we get more inputs on the landscape, the export also tend to increase. However, the second part of the story is due to the hydrological connectivity, because when the year is dry, so there's not enough water to mobilize that nitrogen that is stored in the landscape. But when it rains, then that nitrogen is transported through or flushed through the system. So we can see that when you look at watershed retention capacity, or in this graph, I'm showing the percent retention over time in the Rainprey, and we see that overall, we see a year-to-year variability, but the mean is at 4% retention. However, as I said, the top or the higher retention is in dry year, and the lower retention is in the wet years. So a clear example is this year 2006, which was a 100-year flood, which was a very wet year, and then you see that the nitrogen that was stored in the landscape was flushed and then reduced the retention. So, and this is also when you look at it, the overall period, we see that percent retention has a very strong negative relationship with mean annual discharge, which means that the hydrological connectivity also have a lot to do with retention. So in overall, in this work, we are showing that nitrogen deposition remains dominant, but shows a decline, while we are having steady increase in human waste and fertilizer inputs. We also show that DON dominates the N export, highlighting the importance of monitoring both organic and inorganic form of nitrogen. And we see that nitrogen retention vary with annual hydrological condition. And to reduce the nitrogen pollution, we need both reducing N inputs and also increase or enhance watershed retention by increasing the wetland or buffer restoration that will enhance the retention and also the nitrification. So thank you so much.
Thank you, Clarisse. Next, I'd like to introduce Dr. Wil Wolheim, who will be talking to us this morning about College Brook water quality and planning for its restoration.
Right.
And
This one is
we're looking at.
This is this. All right.
Yeah.
Great. Thank you, Michelle.
Yeah.
Hi, everybody. Wil Wolheim, as Michelle said. We're gonna shift gears a little bit. We're gonna be moving up into a watershed further away from the estuary. But this is an important place for us to think about water quality because most non-point sources of nitrogen, as Michelle said, the non-point sources are dominating inputs now to these watersheds. And most of those are coming into small headwater watershed, just based on the distribution of streams and rivers in the landscape. So I'm going to be focusing on College Brook. I think many of you probably are familiar with this, but this is on the campus of the University of New Hampshire. We're kind of located right along, so this is the Oyster River, this is the tidal part, here's the Mill Pond Dam, and these are this is basically the river network of the entire Oyster River, so showing all the little headwater streams as well. And we're going to be focusing on this red dot, this red line right here, College Brook. College Brook, as many of you know, it flows right through campus, but it's got fields in it. It's got a little bit of forest. It's got campus. It's got town. When we did a synoptic survey of all the different streams that are located in the Oyster River, the College Brook, which is abbreviated here as CLGB, one of the most developed streams in the watershed, as well as one of the streams with the highest nitrate concentrations. This is just based on a grab sample, meaning that we just go to the site and we collect the water sample, bring it back to the lab and analyze it. Usually that's at low flow conditions because those are pretty common. So the other kind of changing gears here is that I'm going to also be focusing much more on what happens during storm events, because a lot of the inputs do occur actually during storms. And as we know, storminess is something that seems to be changing over time. It's becoming more variable. And so it's relevant to understand. So this is actually an aerial view of the College Brook watershed. So this is kind of, we're looking at it from the north, looking south. So here's campus, here's the stadium. College Brook starts up here by the Fairchild Dairy. It flows through hay fields that are manured. There's also some parking lots up here. It enters into the stretch where College Woods is on one side, but then all the athletic fields are on the other. Then it goes onto the campus here. So very developed, very impervious, a lot of impervious surfaces. And then it passes through town here. And then it enters into the Mill Pond down there. So just to kind of give you some sense of where we are here. We've started to monitor, so a lot of the results I'm going to show you today are from these 3 locations along here. So you can see that there'll be sort of different results depending on where we sample because the land use is changing. The other relevant fact here is that there's a lot of stretches that go underground right now, including in every part of the camp. So up here, there's a recreation field. This is just under a turf field. Then it goes under buildings on campus. Then it goes under parking lots on campus. And so this is a very impacted watershed. So what I'm going to talk about today is first demonstrate how water quality looks now, especially during storms. And then what are we planning to do to try to fix this a little bit? So first, obviously, with all those impervious surfaces and fields, the College Brook is very flashy in its hydrology. This red line here represents storms. The flow in College Brook, you can see that it's very spiky compared to this green line here. I apologize for those of you who are colorblind. This red and green. It's much less flashy, and that's typical of impacted watersheds. So we have impaired hydrology to start, which causes a lot of flooding, including downstream along through neighborhoods that occur in Durham. So these are common occurrences due to storms that are fairly typical around here. And when we look at that compared to when you reach a bankful stage, all of these red, this is the hydrograph again here, this blue line. And the top of the hydrograph is shown by dots. And again, if you see this square, these red squares, that means it's been flooding. So the frequency of flooding is very high in this. You shouldn't be flooding this often.
Moving now to the water quality, right? So obviously flow influences water quality. Here, just showing you salt, Michelle mentioned that salt is increasing in these watersheds. When we deploy a data logger in the stream that we can then convert into chloride, you can see that during winters, during storm events, each of these like sort of lines here is during a storm event. You see an increase during the storm event. But then during the summer, you see the opposite. So the base flow remains high, but then you see dilution occurring in the summertime. And we can talk about the mechanisms behind that, but that's like a switch almost. During the winter, it's one way. During the summer, it's the other way. Chris mentions increasing sediments. This is just showing you a storm event that we collected on the campus, showing you how total suspended sediments show this really nice pattern during a storm, going from pretty low during base flow conditions and then spiking almost 2 orders of magnitude during that storm event. And you can see a picture if you walk along the stream during a storm, you see how turbid it gets during that time. And obviously this affects this, then some of this gets down to the Mill Pond where it may settle, but some of it might also get down into the Great Bay where it could be shading the eelgrass. So this is irrelevant for the Great Bay. And then we've also been looking at nitrate specifically. We deploy these high-tech sensors that we can leave in the stream to look at how the nitrate changes during storm events. And here's an example from just below the agricultural fields showing in blue is the discharge during the storm event. And you can see that during this individual storm here, nitrate increases substantially during that time. And this is actually not that common in our region. Usually it's like salt where nitrate gets diluted during storm events. But in this case, even in fall, you see a flushing going on of nitrate. So that also is nitrogen that's probably going to get down to Great Bay where they can circulate and influence what potentially the algal communities and then the eelgrass. And just to show you a couple of other storms here. Oh, this is the turbidity. So now we have a turbidity sensor in there, and the patterns are a bit different. So you know, here this is a storm here, this is the storm here, and you can see how the turbidity spikes, and turbidity is highly correlated with sediments. And the patterns differ slightly with each storm, and that's kind of one of the goals of our study. Jojo Baldus is here. He's my new master's student who's going to be looking at how do these patterns vary among different types of storm events. Similar with nitrate, you see these patterns differ for nitrate depending on time of year or type of storm and things like that. So yeah, so this is basically, all these changes are part of what we call the urban, I add ag because ag is similar, stream syndrome. We have flashy storms that flood downstream. It affects downstream habitats. When you have high storm sediments that scours the habitats and affects light in receiving waters, we have high nitrogen, high chloride, long sections underground, and there's more construction on the way with the new ocean mapping building that's occurring up in the upper part of campus. So how do we restore College Brook? And I want to spend the rest of the time talking about this. I argue we need to invest in our natural capital, just like we invest in restoring our buildings. We need to invest in restoring our streams, especially in the built areas where we live. And UNH has been doing this already. There have been detention ponds for stormwater storage. There's a whole series of them now in the upper part of College Brook, and that's been helping. We're hoping to use some of our data to see how effective they have been so far. But what we're talking about doing here now is to restore a woody riparian zone where possible, daylight the streams where possible. It's not always going to be possible sometimes. And then construct a floodplain to help with those storms that are occurring where you see a spike in flow, a spike in sediments, a spike in nitrate, in order to reduce each of those things. So this is actually an optimal time as well, because if you've seen the new UNH campus master plan, they have made College Brook central to their campus master plan. They want to restore a lot of it. They want to reconnect the campus community to the stream along the entire stretch, although this is kind of the reverse view from the one I showed before. This is the field up here and flowing through campus here. So that's something that it's a good time. And so the restoration area that we're talking about is by the recreation field here. And so what we're talking about doing is there's three phases. We want to restore the riparian zone to a wooded riparian zone in the field here. We want to daylight the stream around this recreation field and create a floodplain wetland that's in a natural turf field right there to store that stormwater. And so this is just showing you some, the aerial photo of the riparian zone restoration. Working with VHB on this, the consulting firm that works a lot in this region. They are designing the restoration, the engineering plan to basically construct a new channel here, daylight the channel here, and then here we're gonna construct this floodplain wetland. We're collecting a lot of data now before zero time. Okay, I'll just finish up with this then. I just want to point out that we're collecting all this data now in order to be able to detect, to quantify the improvements after the restoration. And I'll just end with, we have the funding for the constructing the plan. We got that from the Great Bay 2030 program. Thank you very much for that. VHB is putting together the engineering design, and now we're trying to find the actual money for the construction itself, which is going to be the bulk of the funding. About, you see up there, it's 2.1 million altogether. So we're looking for like 1.8 million or so. If you have any money lying around, let us know. I know everyone's asking for that, but that's the plan anyway. We're working towards it. So thank you very much.
Excellent, thank you, Will. Now, we have time for questions. Lynn, Chris, how much time do we have for questions?
I think we can take about 10 minutes.
10 minutes, okay. So we had some great talks this morning. What do you all have for questions? Steve, I saw your hand go up in the back first.
Yeah, hi, it's a question for Clarisse. How do you assess water quality to attribute manure as a source? I saw that stayed kind of the same percentage over this whole time. We do microbial source tracking in the Lamprey River. We pick up cows a lot. So I'm wondering if there's some way that you can attribute part of the nitrogen input to manure.
Yeah, thank you so much, but that is a very good question, but the way we attribute that to the source of nitrogen from manure is our own process, which start with number of livestock we have at specific area. And then, for example, if you have number of cow or sheep or goats, and then from the literature have shown that if we have this number of cows and with this weight, then the manure from it produces, for example, a specific rate. So then through the number of livestock we have, for example, at county or town or at any scale, then we multiply with that rate that have been.
Question in the back. Allison.
Yeah, thank you. So many great presentations. I'm interested in the phosphorus and salt issues that were raised by a couple of the presenters, and whether there are biotic impacts of those water quality changes that are being observed, or that go along with concentration-based increases.
Will, you want me to take that one first? Sure. In terms of the salt in Great Bay, Great Bay is very salty and, is an estuary. So those salts, I don't think, have any impact there. But in terms of the freshwater rivers, I'm not sure if we have any, fisheries biologists, or maybe Will, you have some more insights as to, how those chloride concentrations are impacting the critters.
Well, yeah, so the levels that we see are, at the level where they do impact invertebrate communities. There are certain thresholds above which certain taxa just can't tolerate. And we are reaching that in a lot of these, headwater streams, and I'm not sure about down in the river itself, but definitely the headwater streams, we're getting some levels that are biologically impairing, the biological community, yeah.
And certainly College Brook has been listed as impaired for high chloride, yeah.
Actually had a study on that. Had a study on that 30 years ago and with an undergrad. And it was very clear that the community composition of the invertebrates was different in the high chloride stream. So it was evident even then, long time ago.
Question over here?
I have a question for both Chris and Wil, maybe relating to the TSS. So, Chris, you were, kind of referring to these upgrades from the wastewater, relating it to TSS, but it seems the TSS is maybe more related to non-point source and, increased flooding. And so I was just wondering if you could comment on how you might better kind of track that in the types of data that we're collecting in the Great Bay and in the headwaters.
Yeah, that's one of the really important things as far as TSS goes, is storm sampling. A lot of our monthly grab samples are directed at capturing these high concentrations that come in storms. So the first step, I think, would be, really looking at how storms are influencing the amount of TSS is getting in. And yeah, so in terms of the wastewater treatment facilities, a lot of these facilities do reduce TSS in the effluent. But the non-point sources are really, I think they're overwhelming the improvements made by the wastewater treatment facilities. So, as far as reducing non-point sources, I don't know, like Wil mentioned, detention ponds, slowing down the water, increasing floodplain areas, just giving the sediment a chance to settle out of the water, I think.
Yeah, no, that's a good question. The non-point sources do seem to be mobilizing, during storm events. And I think that, the restoration plan that we have is sort of, the plan is that an acre wetland that's gonna reduce those storm peaks, which will also store sediments, which should settle out. But then it'll also reduce the power of the stream to further erode the banks downstream as well. So, and because of all these impervious surfaces that we have in the region, we have flashier streams all over, and they are just they create this erosive force. And part of the problem, with the dams as well, the reservoirs are filling in with sediments probably at a faster rate than they would if that wasn't occurring. So yeah, there's a lot going on there.
Have we time for one more question? Nope. Tom.
Question for you,
Oh,
Michelle.
there's a mic right here.
What's up with that? What's up with that increasing phosphate trend? What's that coming from?
I mean, I would suspect it's coming from the non-point sources, just like the nitrogen. But I know that we've seen a lot more, algal blooms in lakes lately, or at least it appears to me, as I see more and more news, news mornings about algal blooms in lakes. And so I think, these freshwater ecosystems are becoming more enriched with phosphorus, and it's likely from the non-point sources. But I will say that I know Rochester is looking at a multi-million-dollar upgrade to address both limits on nitrogen and phosphorus. They're currently not meeting those, so they're hoping to get that improvement to reduce those point sources of phosphorus as well as nitrogen.
Thanks. I'll add that we have a in situ phosphate analyzer that's mothballed that could be available.
Wow.
It wouldn't be plug and play, but it's a seabird hydrocycle, so we can talk about that.
Yeah, great. All right, thank you, everyone.